All right, in this chapter we're looking at the credit risk of an entire loan portfolio, and to start off we need to have a way to measure expected returns and standard deviation in those returns of investing in, first of all, individual loans and then the portfolio. As we talk about the expected return of the loan, things look very similar to what we did in chapter 10. And we have a measure of expected return as a function of what's promised. That's the all-in spread, where we have the loan interest rate minus cost of funds plus loans annual fees. It's very close to the contractually promised rate of return minus cost of funds, except it doesn't take into account compensating balances. And the expected loss here is very similar as in chapter 10, if not the same. It's just that different notation is used. So we're going to define as expected loss being the expected default frequency, or in other words, the probability of defaulting times how much would be lost in a default. So you could think of it as the reverse of the variables we used in chapter 10, where we talked about the probability of repayment and the amount recovered in default. Now, using these terms, we can get the standard deviation in the returns of an individual loan, and it's this formula. Now, you can take it as given that it's the square root of the product of the expected default frequency times 1 minus the expected default frequency, and then all that times the loss given default. I would like to just take a moment to explain where the standard deviation comes from. If you don't really care for derivations or proofs, you can skip over this section. Right. The return of the loan is going to be the all-in spread minus the loss. Now, the loss itself is whether the borrower defaults, and I'll call that D. So it's D1 if there's a default, 0 if it doesn't, times the loss given default. All right, so again, D is going to be just 1 or 0. Now, the only thing that's variable here is this part of that formula. So if I take the variance of this return, it's really just the variance of whether the borrower defaults times loss given default. If you remember your mathematics, a variance, when you have a constant, you can bring it to the outside, and then you have just the variance of the default. Now, the default is follows a binomial distribution. That is the number of defaults out of the total number of loans. Now, the feature of something that follows the binomial distribution is that we can write the variance in this way, where we have the number of times D is equal to 1 over the total times the other outcomes, which is that there wasn't a default. Now, this is the expected default frequency. That's 1 minus the expected default frequency. And so therefore, the variance of the returns is the square of the loss given default times the expected default frequency times 1 minus the expected default frequency, and then of course the standard deviation would be the square root of that. All right, so now bringing in the folks who didn't care to see that proof, There's always people who are curious and can't take a formula at face value, so I felt like I had to give a little bit of an explanation. The next variable that we have to discuss is correlation. So we're going to talk about the correlation of returns of loans I and J. Now, one feature to recall about correlation is that it is mathematically possible to be outside of this bound of -1 and +1. Also, it's helpful to remember that we can also write the correlation instead of the Greek letter rho. We can write out cor, and it's the correlation of actually these two returns. Let's define the weight of loan I as the dollar of amount of loan I divided by the total loans. So it's really the same as any portfolio weight, where in this case, instead of portfolio of stocks, we're talking about portfolio of bank's loans. Now, with given these variables, we can, given two loans, right? So we're just going to do two loans here in our portfolio. The formula for the expected return of the entire portfolio will be the expected return of loan 1 times its weight times the weight of 2 times the expected return of loan 2. Now, when you have only two, it's very helpful to keep in mind that the weights have to sum up to 100%. So if you know the weight of one, you know the weight of the other. Right? That's very important to remember. Now, to get the standard deviation, it's easier to first find, or actually required that you find the variance first. So the variance of a portfolio of two loans would be the square of the weight. This is a review of things that I know was discussed, at least in the introductory finance course. And then we have to remember this interaction term at the end. So 2 times the product of the weights times the correlation times the standard deviation of the two loans' returns is this variance, and then to get the standard deviation, again, take the square root of that. So we'll be using these formulas. Remember again, the weight of 2 can be replaced with 1 minus the weight on 1, since we're only talking about two loans. Now, we can put together these two statistics to calculate something called the Sharpe ratio. The Sharpe ratio is the trade-off of reward from taking risk and the amount of taking risk. So you see in the numerator there, it's the expected return of our risky portfolio minus the risk-free rate. So this is the expected gain over taking no risk. And then it's divided by the risk, which is the standard deviation of the portfolio. Now, if in modern portfolio theory, we always select a portfolio so that the Sharpe ratio is maximized. So likewise, the bank manager should select a portfolio of loans that maximizes the Sharpe ratio. And so we're going to, so we have a thrift that has two kinds of loans. And we're actually going to treat the loans as the two types of loans as portfolios themselves. And so the decision is how much to invest in each portfolio. We have conforming residential mortgages. By conforming, it means it meets the lending standards of Fannie Mae and Freddie Mac, the GSEs. And so that means that the credit quality of the borrower is above a certain level. If it doesn't meet the requirement, then it would have to be a subprime loan. And so not surprisingly, the subprime mortgages have the higher interest rate. We're going to assume cost of funds are the same, fees are the same. Notice the loss given default are assumed to be different. So the higher credit quality borrowers default, we're going to assume that 80% can be recovered, whereas only 60% will be recovered for the subprime. And the higher quality borrowers will have an expected default frequency of only 2%, whereas subprime 8%. So if you look at the previous page, we're going to apply the formula for the, first of all, the expected return of the two kinds of loans. So we're going all the way back. Let me just show you. We're going back to the very beginning. We're doing this part first, and then we're going to do the portfolio math. So the expected return of residential mortgages will be the interest rate minus cost of funds plus the fees. So that's the all-in spread minus the loss given default times the expected default frequency. So I'm going to make the EDF decimal and loss given default percent, because you can't multiply 2%, because then the units would be all inconsistent. And when you calculate these numbers, you'll get 3.1% there. Same thing for subprime. Giving you 5.8%. Now let's do standard deviation first. For deviation, we'll do the expected default frequency of 0.02 times 1 minus the default frequency, which is 0.98. Multiply that by 20%, giving us 2.8%. And for subprime, we have a default frequency, expected default frequency of 8%. 1 minus 8% is 0.92%. Square root times 40, giving us 10 point, and I'm going to round to a few digits, 10.8517%. Alright, so I recommend that you maybe perhaps pause it here, go back to the formulas, make sure you understand where I'm getting all the numbers, how I'm plugging them in. If you have any confusion about percents, take a moment to think about it. And then if you're not understanding why I left some numbers in percents and why I didn't, then ask me about it during our live session. Alright, now given these numbers, we're going to calculate the expected return of a portfolio with 80% conforming mortgages and 20% subprime mortgages. So the expected return portfolio is 0.8 times 3.1% plus 0.2 times 5.8%, giving us an expected return of 3.64%. Let's first do the variance. So this one has all the many terms. So weight squared plus variance, weight squared times variance, and we're going to use a correlation coefficient of 0.05 multiplied by standard deviations, and that will give us 10.2142. Notice that's not in percent, but when I take the square root, only one of the percents will be left over, and I get 3.1960% for the standard deviation of this portfolio. Now, if the risk-free rate was the Sharpe ratio, so plugging into the formula for Sharpe ratio, we have the expected return of the portfolio minus the risk-free rate divided by the standard deviation, giving us a Sharpe ratio of 0.83. Now this is what we would compare other portfolio Sharpe ratio to, and we would want to select the portfolio that would maximize that number. So there could be another portfolio besides this arbitrarily chosen one of 80%, 20% that would give us an even higher Sharpe ratio. Whatever gives us the maximum will be the portfolio we should pick. Now I'm just going to tell you that after finding the maximum Sharpe ratio for these particular mortgages, these particular kinds of loans, that the weight on the conforming mortgages that would maximize the Sharpe ratio will be 87.45%. So you can just take that as given. I did the calculation that that is what would maximize it. Well, so let's look what the Sharpe ratio would be with those weights. So just to help you see how that fits in to our formulas, the weight on the conforming mortgages would be 0.8745. The weight on the subprime would be 1 minus that, which is 12.55%. All right, and then we're going to have to do it over again. And that gives us 3.4389% for the expected return. For the standard, well, first of all, for the variance. So you can see these calculations are pretty intensive with all the numbers you got to keep track of. And the variance will be 8.1839. And when you take the square root, you'll get 2.8607, giving you a Sharpe ratio of 3.4389 minus 1 divided by 2.8607, which is 0.85. And so we can see that that will be higher than this arbitrarily chosen one previously, where it was an 80-20 portfolio. Now, our conclusion about putting 87.45% in the conforming mortgages and 12.55% is based critically on the correlation assumption. Now, what if it turns out that the correlation is actually 0.55, but we thought that the correct correlation was 0.05? Well, a few things. So that's a subprime. That's the conforming. If I plotted these numbers on a graph of the expected return against standard deviation, the Sharpe ratio would be the slope of this line that's tangent there. That'd be my optimal P. Now this is the line assuming that correlation is 0.05. Now, if the true correlation were something higher, like 0.55, then the portfolio that would maximize, no, I'm not drawing it super terrifically there, would be different. And we would have selected probably more of the conforming mortgages and less of the subprime. Let me just tell you that after doing all the math, that the best portfolio under a different correlation coefficient would be 98.5 conforming So almost no subprime. The portfolio we picked might be, let's say, there, and that would have a lower Sharpe ratio than this portfolio. The point that I'm trying to make is that if we make a wrong assumption about correlation, then we could make a wrong decision about what to invest in. And this was one of the mistakes that was made that led up to the financial crisis, where lenders and investors in mortgages wrongly thought that the correlation across default rates was very low, if not zero. But in reality, we found out that it's actually much higher. If they knew that, they wouldn't have made so many loans in the subprime segment of borrowers, and actually wouldn't have created as much of a problem because there wouldn't have been this over-lending to borrowers that were going to default that would then precipitate defaults. What you have to be worried about on your own, you are going to do this. Okay, you're going to be given a weight for conforming mortgages, so besides the ones that were given here, and you'll have to enter your answer on the online quiz. So I recommend just follow the steps that you see here and here, basically using the same formulas, just two different numbers. Follow the steps carefully. Talk about another way to control credit risk of an entire loan portfolio, and that's a loan volume based model. So what we want to do is prevent the bank from investing too much into any one kind of loan, because if that loan defaults, then it's going to be this huge part of the portfolio of loans and will impact the entire bank's portfolio. But if they're diversified across lots of loans, if any one loan or category of loans fails, then the other loans are performing and the risk is reduced. So it's really all about the idea of diversification. Again, now we're going to make an assumption that the national portfolio here is optimal. Kind of like the market portfolio when we think about CAPM and stocks. Now, even though I'm using the Greek letter sigma here for this concept called deviation, this is not standard deviation. Rather, it's deviation from a national aggregate. Now, the formula is, we're going to take the portfolio weight for Bank J in loan category 1, subtract it from the portfolio weight of the national aggregate weight, and square it, and do the same for loan 2. Right up to the very last loan category that I'll call N. And then we'll divide all of that by the number of loans. Right? So this is the square root of all of that. Now you might wonder, where does this formula come from? The intuition is, if you think about the Pythagorean theorem, from point 0 there, so you have a base of B, height of A, hypotenuse is C. The distance between these 2 points is the square root of the squares of those 2 distances. And if you extrapolate this to beyond 2 dimensions, to n dimensions, then that's what this deviation is telling you. It's telling you a distance from that the bank has in its loan portfolio from the national aggregate portfolio. All right, let's do the example and then everything starts making more sense. So we're going to look at the banks that we've been working with this semester: Bank of America, Old Line Bank, WesBanco, and then we're going to look at the whole U.S. So here are the 2018 loan values from their balance sheets, from their call reports. And we're first going to find the weights. So for Bank of America, we're going to take 245,866 here, and then we're going to divide it by its total, which is here. So notice what I'm dividing by. I'm dividing by the total in the row. And that first weight will be 26.16%. And then do the same thing for commercial. We'll divide 340, that's actually 340 billion by 939 billion. And when you do that, you'll get 36.18%. So I'll leave it for you to confirm that you can get these numbers. 172 divided by 939 is 18.3. 18.29 of other. Notice that these categories are very broad. In practice, for us to use this model, we would need to be more specific, like industry, but the call reports don't report the loans broken down by industry. So to explain the concept, though, I'm just giving these very broad categories. The management will know much more detail. And now we'll do the same thing for Old Line Bank. We'll do 503 divided by 2429. And Old Line's investment in residential mortgages is 20.72%. And then we do 1.6 billion divided by 2.4 billion. That's 6.55%. 49 divided by 2429 is only 2.02%, and then 260 divided by 2429 is 10.71%, and again they'll sum up to 100% of the loans. You have to do WesBanco's weights on the quiz, and that's going to feed into calculating the deviation. So I'm going to skip that now. Let's do the total US. We're going to divide 2.2 trillion by 9.392 trillion. And let me just give you the final numbers there, because these numbers are starting to get pretty big. 3.59%, 46.55%. Again, 1.47 divided by 9.39 is 15.73%, and then others 14.13%. And of course that sums up again to 100%. Now we're going to use these percents here in the formula I gave up above. So the deviation for Bank of America will be Bank of America's portfolio minus the US aggregate, which is 23.59 squared. Let me just point out where that came from in the table for a moment. So I took Bank of America's 26.16 and then subtracted from the 23.59. And then the next step, I'm going to take the commercial Bank of America, subtract it from the US aggregate commercial. So we have 36.18 minus 46.55 squared. just make it like this so you can see where it is on that table. You get 18.30 minus 15.73, and then 18.29 minus 14.13, and then divide all that by the number of loan categories here, which are 4. After you plug that all into the calculator, you'll get 5.87%. Right? And then we'll do the same thing for old line. So we're going to take 20.72 minus 23.59, C6.55 minus 46.55, and so on. And so that you'll have to look at your printout or your notes there, because I can't fit them all in to one screen, so I'm writing it. So this is the residential, and then we have commercial, and we have consumer. Notice old line has very little consumer in comparison to Bank of America and the national aggregate. I'm also noticing as we're writing this that it has very little consumer. I mean, it has a lot more commercial. I'm going to divide all of that by the number of loan categories, which are 4, take the square root of all of that, and we get 12.33% deviation. So if you think about, again, this deviation as something akin to a distance, we see that Bank of America's distance from the national aggregate is much closer than old line. I think that can make some amount of intuitive sense in that Bank of America is the largest least deposit taker in the country, and you would think that it would match more of the entire national aggregate, whereas old line is a state bank, relatively small amount of assets, doesn't have the ability to diversify as much as a bank like Bank of America. Now, again, this is what you're going to do on your own. So everything on this page you're going to do on your own in quiz number 4. You're going to get the deviation of WesBanco, so it's going to require you to get the percentages here, like I did with these other banks in the US, and then you're going to take the difference of WesBanco from the US in each category, take the square root as I did here, to get the deviation. I would like you then in number 2 to add the numbers for old line and WesBanco. Recall that we found out that a year after this call report, Old Line Bank and WesBanco merged. So, as is explained here in your notes, it's common to anticipate what the impact would be of a merger by looking at the pre-merger numbers together as though the bank were one entity and see what would it look like. Of course, we don't know what the future holds, but by at least combining what it would look like in the past, it gives some indication of what it would look like in the future. So it's called the pro forma number. So, repeat what you did for WesBanco by itself. With WesBanco plus old line, calculate the deviations, report that, calculate the deviation, and report that. And then something for you just to think about before our live class is, what do you think about the numbers when you look at the deviation of WesBanco versus the deviation of old line versus the deviation of the pro forma combined entity? All right, I just want to make a little bit of a quick comment about some other models. This is only going to be brief. If we had some data on what the loss rate would be, we could make a scatter plot. Given total losses of an entire loan portfolio, and then losses of that particular category of loans. So let's say we do that data and we draw a trend line. And I kind of think that that would look like the trend line. There would be an intercept, we'll call that alpha, there'd be a slope, and that would be called beta. And so we could fit this equation. And so the way you would use this would be loans with higher beta should have lower concentration limits. So if there's a type of borrower that tends to default much more when an entire portfolio of loans are defaulting, then that would be one where you would impose some limit. The bank management would say, we're not going to lend above X% of our total loan portfolio to that kind of borrower. Whereas if another borrower is more insensitive to the performance of all loans, then it's safer to lend more to that borrower or that type of borrower. Just want to point out to you, I've posted 2 files to talk about how concentration limits are determined. And so, first of all, subjectively, and that I think is probably more practical, is look at the Federal Reserve's guidance for bank examiners in seeing, for testing whether or not banks have are controlling for concentration risk, and which means the risk that of an entire loan portfolio performing badly because of not being diversified. And it's only about two or three pages, so I think it's worth reading to get a sense of practically how do you implement these ideas by a bank regulator. And then we have the quantitative-based models, and this Bank of International Settlements article, or it's almost more of a research paper I posted. This is a bit more advanced, actually not a bit, it's significantly more advanced than the guidance from the Federal Reserve. But I put it up there if anyone is interested, and it just talks in detail about these quantitative models and gives a summary of how really it's just going to be the very largest banks could be implementing these more of a quantitative method to controlling for loan risk. One thing to keep in mind is that we might, if we limit the amount of loans a bank makes, remember they're delegated monitor, which incurs significant fixed costs, so there needs to be scale. So what's the point of limiting your lending to a particular kind of borrower at, let's say, 1% in order to be diversified? Really abstracts from what the bank is doing, in that it has to expend a significant amount of cost to know about that kind of borrower and to monitor them. If they're going to be putting in that amount of expense to screen and monitor loan applicants, then they should probably make a significant amount of lending in that area to make it worth all of the expense, because a bank can't be an expert in everything except for the very largest banks. So for a small bank, there's that consideration of scale and how practical it is to limit the concentration in one kind of borrower.